There are 1,000 grams in a kilo, 16 ounces.
All right, today we're going to be talking about measurement and significant digits, sometimes called Sig Figs, sometimes called Sig Figs for significant figures that mean the exact same thing. So just some simple review. What is mass? It's how much matter is in an object. How do you measure mass? You, in this class, are going to get to use electronic balances. So the units will be in grams, and they go out to the hundredths place. Volume, look at this bubble here that she blew, is how much space is occupied by an object. And if you're trying to find the volume of a liquid, how much space the liquid takes up would be measured in milliliters, and you would use something called a graduated cylinder. Couple of questions about this. Water, for example, will form this curved line. What is that called? You may remember that term. It's called a meniscus. Another thing that's important to talk about is, do you measure something from the highest part or the lowest part of the meniscus? And the answer is you always measure from the lowest point. Okay, so how much water is in this graduated cylinder that's in the picture here to the correct number of significant digits, which we're going to learn about right now. So it goes 41, 42, 43, and the top of the meniscus is about halfway between the 43 and the 44, but we're right at the 43. So we can't say, for example, that this is 43.00000. We don't really know it with that much significance. We also don't want to just say 43 because we're better than that. Since it goes by the ones place, we estimate out one more digit. So I would estimate this to be 43.0 milliliters. All right. What about if you have a regular solid, for example, a cube? The units would be centimeters cubed, and you would just simply use a ruler to measure the length times the height times the width of the object and multiply them. We do not do that in this class. Most of the time we're trying to find the volume of an irregular object. So how much space does an irregular object take up? And you've probably done this displacement technique before, where you fill something up to a certain point with water. You take note of that. You add the object in, and what you really care about is the difference between where the water level was before and where it is now, because that difference will tell you how much space that unknown object is taking up. Okay, so for example, this one, the water ended up at 2.40 milliliters. It started at 1.65 milliliters. Do a simple subtraction. We know that this little black rock is taking up 0.75 milliliters of space. And again, the tool for that technique, water displacement, is a graduated cylinder. Okay, so this is kind of a fun story. According to legend, back in ancient Greece, there was a king who had given a bunch of gold to someone to make him a crown. And he suspected that someone gave him a fake gold crown, just plated it in gold. So Archimedes, one of the best philosophers of that day, was given the task to figure out if this crown was actually real or if it was fake. It seemed impossible at the time to figure out. So this story about Archimedes is that he was in the bathtub and he noticed that when he got in, the water overflowed. So he said, okay, if I can figure out how much space something is taking up, I can actually just use this water displacement technique. So the legend says that this gave him the idea of how he could figure out if the king's crown was real gold or not, and he was so excited that he leaped out of the bathtub and shouted, "Eureka!" And he forgot that he didn't have clothes on, and so he was running through the town naked. Okay? Well, Archimedes was right. So you can find the density of an object if you know its mass and how much space it takes up. Okay? And every object, or every material, I should say, has a unique density depending on the size of the atoms and how closely those atoms like to be packed together. we call it the amount of mass per unit volume. And down here I have a picture. Here's metal A, here's metal B. Which one would have a higher density? Hopefully you would say metal A because those particles are packed closer together. Okay, so what Archimedes said, you can find the mass of an object by putting it on a balance. Luckily we have electronic balances. You can put an object in water to find out how much space it takes up, measure that change in the water level, and then once you have the mass and the volume, divide to find the ratio of those, and no matter how big an object is, small piece of aluminum or a really big piece of aluminum, that ratio of the two objects will stay exactly the same. Okay? I like to have students remember this by knowing that you love density. Okay, so density D equals mass divided by volume. And you can see it kind of looks like a broken heart there. Okay, but that'll help you remember the formula. Mass divided by volume gives you the density. Now, this chart helps people who are math challenged. What you do is whatever variable you want to solve for, you cover it up. Okay, so if you're looking to solve for density, cover it up. Mass divided by volume is how you solve for density. What if you want to solve for mass? You're given the density and the volume in a problem. Well, you cover up mass and you do density times volume to get your answer. And if you want to solve for volume, you do mass divided by density. And I'm going to show you how those units cancel out here. Okay, so the units for mass are grams. So if you take density, the units are grams per milliliter, and you multiply it by volume, the units are milliliters. Notice that milliliters over milliliters cancels out, and you're left with grams. Okay? What if you are solving for volume? Volume, the units are milliliters. So we would want to do mass, which is grams, divided by density, which is grams over milliliters. Grams cancels out, and now you have 1 over milliliters. Well, if you have 1 divided by 1/2, you can punch that into your calculator. You get 2. That 2 flips up to the top. So 1 over milliliters is the same as milliliters. So you can see how those units cancel out and work out. And then finally, the simple one, density, mass divided by volume, that's grams divided by milliliters. So the units for density are indeed grams divided by milliliters. All right. Let's do a couple example problems. What is the density of an object that has a mass of 6 grams and a volume of 3 milliliters? Okay. We know density is mass divided by volume. We know the mass is 6 grams. We know the volume is 3.0 milliliters. So my answer would be 2.0 grams per milliliter. Now, you may wonder, why didn't I just say 2? Or why didn't I say 2.00000 grams per milliliter? Well, when you're counting up your significant digits, this has 1, 2, 3, this has 2. You can only know your answer to the fewest number of significant digits when you're multiplying or dividing. So that means your answer should have 2 significant digits. Okay? What about this problem? What's the volume of an object that has a mass of 10 grams and a density of 2.5 grams per milliliter? Okay, we want to know volume. So we can switch these two. You can go back and use that circle chart if you like that. But volume is mass divided by density. So in this problem, we know our mass is 10 grams, and we know our density is 2.50 grams per milliliter. 10 divided by 2.5 is 4, but this has 1, 2, 3, 4 significant digits, and this has 3, so our answer should have 3. 4.00 milliliters. Grams cancels out. 1 1 over 1 over milliliters. Those milliliters flip to the top. The volume would be 4 milliliters. All right, last example problem. We're looking for mass. Okay? So mass, if we're solving for m, equals density times volume. Density is 2.5 grams per milliliter, and the volume is 10.00 milliliters. 2.5 times 10 is 25. This has 2 significant digits, this has 4, so our answer can only have 2. Milliliters cancels out. Answer, 25 grams would be the mass. Okay, and we've already touched on this, but talking about what digits are significant when you're taking measurements or when you're solving for density can be kind of crazy. There are actually a lot of rules, and if you take AP Chemistry, you will learn all those rules and hopefully know them very well because they affect virtually every answer in chemistry. But when you're measuring, I mentioned this earlier with the graduated cylinder, you always read as many places as possible from the instrument and then estimate one additional place. The last number is always the one that you're uncertain about, your guess. Okay, so there's a little practice here. Which digit is uncertain in each of these measurements? And it's always the last digit. So 43.29, it's the 9. 23, it's the 3. 184.2, it's the 2. Okay, example. What if you have an instrument that reads to the nearest 10th place? Well, if you've got something that reads, let's say, 1.2, you wouldn't record that. You would actually estimate to the 100th place. Okay? What if a scientist records a measurement as 23.4? Well, the 4 is estimated, so the instrument must go by the 1's place. How long is this object? Okay, well, let's look at the instrument first. The instrument is going by 0.1s. 0.1, 0.2, 0.3, 0.4, 0.5. Okay, 1, 1.1, 1.2, 1.3. So it looks like to me it's between the 1.2 and the 1.3. So you wouldn't want to just say, oh, I think it's 1.2, because that's already what the instrument is measuring by, the 10th place. So you would want to estimate out one more digit. So maybe 1.25 centimeters, for example. Well, you could really say anything instead of that 5, and you would still be just fine in your answer. Maybe you said 1.23, maybe you said 1.27. Okay, because again, that last digit is uncertain, and so it's not going to match maybe your lab partners. If markings are given every 10 milliliters, then you estimate to the 1's place. If readings are given every 1 milliliter, you estimate to the 10th place. And if something is given every 0.1, you estimate to the 100th place. So that's kind of a nice big overview there. Okay, there's some odd cases. Sometimes our graduated cylinders, for example, read by the 0.2s. Still estimate to the 100th place for those. And if you've got an instrument where the markings are only every 25 milliliters, 50 milliliters, or worse off, every 100 milliliters, it's a kind of a trick question. Just don't use that to measure. Okay, if you do use it, then your measurements should be not like 90.0. Okay, they should be very generic. Okay, but you really shouldn't be using that. All right, that's it for our measurement and significant digit notes.